Okay, so here we talk about the induction and energy transfer. So here is another setting or experiment related to the magnetic flux changing related to the Faraday's law. Okay, so here it says a rectangular loop of wire with L has one end in the uniform external magnetic field that is directly perpendicular into the plane of the loop. So here only in this area we have a magnetic field which is uniformly over this area, but outside this area we assume the B field is perfectly zero. Okay, so this is the assumption. Okay, so here is try to pull out this rectangular from the magnetic field. So you can see this is the velocity pointing to the right side. So in that case, as much as B is a constant value, and then you can see that the cross-section area will become smaller and smaller because the guy is pulling this loop out of the B field. So A is decreasing. So in that case, the magnetic flux is decreasing. Okay, so this field might produce a large electromagnetic, by a large electromagnetic. So the dashed line in the figure shows the assumed limits of the magnetic field. The fringing out of the field as its edges is neglected. So you are to pull this loop to the right of a constant velocity v. Okay. So of course, according to the Faraday's law, there will be induced current and also induced EMF. So what is the direction of the current? Of course, it already tells you that the current is clockwise. So let's see how we can determine it with Lorentz law. So here we can see the B field is pointing into the page, and here we try to drag this loop out, which means that the magnetic flux pointing into the page is decreasing, which means that B induced should be pointing into the page to compensate this magnetic flux decreasing. Okay, so this is B induced. So using right hand rule, you use of thumb pointing into the page. Your finger will be pointing the clockwise direction. Clockwise for AI and also I induce and also E induce. Okay, so here we have I pointing to this side, I pointing to this side, I pointing to this side. Okay, so as much as we have current and also we have magnetic field, there will be force acting on this wire due to the Lorentz force, or the second version of the Lorentz force, which is I times L cross B. I times L cross B in chapter 28. Okay, so here, let's consider this wire first. So this wire, we have I pointing to the right side, which means that for this wire, L also pointing to the right side. And then L cross B. L is pointing to the right side, B is pointing into the page. So we have F2 pointing upward. For this one, it is out of the B field, so there is no force acting on it. And then for this wire, okay, so actually, the current is pointing to the left side because it is clockwise. So this L is pointing to the left side. Although this is L, this is also capital L, but yeah, we use capital L for that one. So just keep this notation here. So here for this wire, L is pointing to the left side. Of course, when we really want to calculate the value, we only consider L is as long as this one. Because we don't have B for this part, so we only calculate B for this part, L for this part only. but here we only consider the direction. So L is pointing to the left side, and then B is pointing into the page. So L cross B is pointing downward. And then for this one, L is pointing upward. L is pointing upward. B is pointing into the page. So L cross B is pointing to the left side. So here for the whole loop, we have F2 pointing upward, F3 pointing downward. And we will suppose F2 and F3 have the same magnitude and pointing to the same the opposite direction, which means that F2 and F3 will cancel each other. So the only force acting on the loop should be F1, which means that when you try to drag this loop out, there will be a force pointing to the opposite side to stop you from dragging this loop out. Okay, so in that case, there will be flux changing. Therefore, a magnetic field and a conducting loop are in relative motion as bit V, and the flux of the field through the loop is changing with time. Yeah. Just as I mentioned, because you are pulling the loop out of the magnetic field. Okay, so there will be rate of work. The rate of work is nothing but F times V, because when you learn mechanics, which is like F times S equals W, or generally W is integration of F dot ds. This is the work done. This is the work done by the force. So F dot ds line integral will be the work. Okay, so the power is dw dt. To take the derivative of the work with respect to time. So it is like integration of F dot ds dt, something like this. Okay, so and we assume that f is a constant, so we only take the derivative of s, so it finally becomes f dot v or f dot dv, something like this. So it turns out to be f times v or f times v. Okay, we just assume it is uniform everywhere. So finally it becomes f times v. But of course, in this case, v is a constant value, and f is also a constant value, so it's like f times v. Okay, so here we try to do some calculation. So phi b is the magnetic flux, which is B times A, and we will consider the width inside the B field is called x. It's called x, and then L is the height of the rectangle. So phi b is B times A. So B is a constant. So we have B times L times x. So L times x is the area. So here we have phi b, and then we can try to apply Faraday's law. So this is the magnitude of the EMF, E equals d phi dt. So we just plug in this one into here. B and L are independent of to the time. So B times L and then dx dt. dx dt is the derivative of the displacement, which is the velocity. So E is BLV. E is BLV. Okay, so far we have E equals BLV. And then on the other hand, we have I equals E over R. So this is nothing but the Ohm's law. So we have EMF, and also we have resistance over the loop. So yeah, so I equals E over R, and then we plug in this E into here. So I equals BLV over R. Of course, this V is not voltage, so be careful. This V is the velocity of the dragging the loop. So the deflecting force acting on 3 segments of the loop. Yeah, so as I mentioned, F2 and F3 cancel, and then the only force is F1. The only force is F1, and here we can also have F equals F1. F equals F1 because we assume that V is a constant velocity, which means that F and F1 is actually has the same magnitude but in opposite direction. So we have F equals F1 equals I times L times B times sine of 90 degrees because L and B are perpendicular to each other. So which means you have sine of 90 degrees, which is 1. So F equals ILB. So this is ILB. And in the previous page, we already have I equals BLV equals R. So we just plug in this one into here. So we have BLV over R times LB. So we can just correct the same terms. We have B squared, we have capital L squared, we have V over R. So this is the expression of F. And finally, P equals F times V. So we multiply another V. So we have a BLV whole square over R. So this is the power consumed by the loop. And it mentioned that the work that you do pulling the loop through the magnetic field appears as thermal energy in the loop. Okay, because it's just consumed by the resistance. And if it is consumed by the resistance, it will generate heat in this procedure. So when you try to pull this loop out of the B field, you feel that there is another force dragging the loop back, and then you will also find that there will be some heat generated. Okay, so here it talks about the eddy currents. In Chinese, it is called 涡电流. So just now we have a physical loop there, so that there will be current. And here it mentioned that even though it is not a explicit loop, there will still be current. So here it's like a conducting plate. So there is no predefined loop there. Okay. But here it says, as you pull a solid conducting plate out of a magnetic field, there will be eddy currents induced in the plate. A typical loop of eddy current is shown here. So if you have a conducting plate and then you try to pull it out from the magnetic field, there will still be eddy current. Not necessarily this path. There may be a complicated situation. And how it acts, if you really need to know how it acts, you really need to use some EM simulated software to do so. And then, of course, you would draw out something like a rainbow map with different color of level to tell you which part has larger current, which part has smaller current. But the phenomena will be quite similar to the previous case like this. So if you try to pull this thing out, there will be a force dragging your plate back. So there will be a force pointing to the right side if you try to move this thing out of the B field, and then still there are some current rotating inside the plate. And then of course it will also generate some magnetic field pointing into the page, because if you try to draw it out, then the magnetic flux is also decreasing. So B induced should also pointing into the page to try to cancel this kind of a change. Okay, so here we talk about the real form of the Faraday's law. So just now, when we see the Faraday's law as E equals negative n d phi b dt. Okay, so here, rather than writing it as E, we try to write it as this expression. Okay, so yeah. So this is a line integral similar to the Mps law. For the Mps law, it looks like this: integration of b dot ds equals mu times I enclosed in chapter 29, if you still remember. So for this case, we have this expression, integration of E dot ds equals negative d phi b dt. Also similar to Faraday's, the Gauss law. When you learn Gauss law, it is something like this, Q enclosed. And if you just express this one as phi E, so it will be something like epsilon naught times phi E equals Q enclosed. Something like this one multiplied by this one is this one. Something like F equals MA, but yeah, this is not good to use, so we just write out this phi E as a double integral. Here we also write the EMF as this one. And this is a line integral. Okay, so here it says using the induced E field, we can write Faraday's law in its most general form as this one. So yeah, so a changing of magnetic field produces an electric field. So we will induce electric field and also EMF and also induce current. Okay, so here we need to have a note that when we learn chapter 24 about the electric potential, we have V. At that time, we know V equals negative integration of E dot ds. At that time, it tells you that the voltage difference at that time, the potential difference, the electric potential difference, or sometimes I just call it the voltage difference between these 2 points, only related to the initial point and the final point only. It doesn't relate it to the path. So when we have a closed loop, then V should be 0. But here, this closed line integral is not 0. This one is not 0. So because here we have the change of magnetic flux, when we talk about chapter 24, we don't have the idea of B field yet. So if we don't have B field, then we can be comfortable to apply the concept of electric potential to simplify the calculation. But here we need to pay more attention. As much as we have magnetic flux changing or B field changing, then this closed line integral is not 0 anymore. So yeah, so when we have magnetic field changing or B field changing or magnetic flux changing, then try to avoid using the concept of electric potential. Otherwise, you may make mistakes. You may consider, oh, this is nothing but 0, so all of them are 0. Then yeah, just wrong. Okay, so electric potential, induced electric field are produced not by static charges, but changing magnetic flux. Therefore, electric potential has meaning only for E field that are produced by static charges or static charges. It has no meaning for electric field that are produced by induction. So we have the concept about EMF, and then we need to tell you that there just now we have the EMF for a loop. Yeah, we have an EMF for a loop. So you need to determine which side is higher. So actually you can consider the battery to be an EMF, but not the other way around. You should not try to change this E induced into a battery. Sometimes it might be correct if you just consider it as a model, but that is not the exact case. So if you just consider a battery to be an EMF, it will be still correct. But if you do it the other way around, it may make mistakes. So yeah. Okay, so here we try to explain about the Faraday's law. Okay, so here it says here we have a copper ring. We have a copper ring. So so this is the copper ring or copper plate or copper wire. Okay, so maybe we have B field pointing into the plate. This is a copper ring. This is a copper ring. Okay, so the red one is the copper ring, and then here we have magnetic field pointing into the page. We also assume that the B field is changing, rather either increasing or decreasing. Just talk about it later. So we assume that we have B field pointing into the page in this area, and then the red line is the red circle is the copper ring. Okay, so here if the B field is increasing, it will induce the E field for this ring here. It will induce the E field. Okay, so in that case, if we just put the copper ring there, of course there will be current going through the ring. But even if we don't have the copper ring there, we will still generate some E field in the space. So let's see. Here it says, if the magnetic field increases at a steady rate, a constant induced current appears in the copper ring. So there will be induced current appear there. Okay, yeah. Okay, so we can actually define the direction of the current using Lorentz law. As I mentioned, the B field is pointing into the page, and here we assume the field is increasing. So the B induced should be pointing out of the page. B induced should be pointing out of the page. So using right-hand rule, you use a thumb pointing out of the page. The thumb is counterclockwise. So this is the direction of the EMF, which is this one, and also the current, the direction of the current. So the current should be counterclockwise. Okay, so for part B, an induced electric field exists even when the ring is removed. So it will generate E field there. And actually for different radius, it will still generate E field, but of course with different magnitude. So for the part closer to the outside, it is stronger. For the part closer to the to the center, it is weaker. Okay, so yeah, so it relates to the radius to the center, but still we can we can conclude that the all the E field have a similar direction for different circle. For the different concentric circle. For example, if you just draw a line here, then all these points, for all these points, the B field are pointing downward. And then, for example, if we draw a line here, then all the B field there are pointing that side. So it's just like using right-hand rule to determine the direction of the induced E field. Okay, so the complete picture of the induced E field displays like this. So it has even outside this area, it still have E field, induced E field. The reason is that how do we determine this part and this part? So for example, if we try to determine the path as this red one, then d phi b dt only consider these parts. So for different radius inside this area with the magnetic field, the whole circle counts on the magnetic flux, But here, if we just define the this is so-called the Mps loop, the outer one is the Mps loop. Here when we consider the magnetic flux changing, so it counts only on the yellow area. So even though the circle, the Mps loop is as large as this one, it still counts towards the yellow area. But at least it is not zero, so we still have induced E field outside the yellow area. But of course it will be smaller and smaller because the loop is longer and longer. Okay, so here it says four similar close paths that enclose identical area, equal EMF are induced around path 1 and path 2. So here it says for this one and this one, because we consider the B field is uniform inside this area, so we assume that these two areas are actually the same area. Of course, the direction slightly rotate, the shape is slightly rotate, but these two shapes are actually the same. Okay, so here it says d phi b dt or negative d phi b dt for area for contour 1 and contour 2 are exactly the same. Okay, so similar close path that enclose identical area. So equal EMF are induced around path 1 and path 2. They share the same negative d phi b dt, which means that E1 should be equal to E2 equals to negative d phi b dt. Okay, so which lie entirely within the region of the changing magnetic field. A smaller EMF is induced around path 3, because here path 3 is here, so part of them is not covered by the B field. So here only this part only these parts contribute to the magnetic flux, which means that this magnetic flux is smaller, so the magnetic flux changing is also smaller. Okay, so for the path 3, a smaller EMF is induced, which only partially lies in the region. And then for path 4, this is totally out of the B field, so no net EMF is induced around path 4, which lies entirely outside of the magnetic field. It doesn't mean that there is no E field outside. There is still E field outside, but here it only means that for integration of E dot ds for the path 4 is 0. Is 0, which means that if you try to cut this path into many small segments, and then you try to calculate E dot ds for every small segment, and then you try to add them together using the Riemann sum, so you can get this integration of E dot ds for the contour path 4, and then it should be 0. So which means that part of it is positive, part of it is negative. And then the positive part and the negative part perfectly cancel each other because of the Faraday's law. Okay, so yeah, so this is something similar to what we learned the Gauss law. So when we consider what the magnetic flux, whether it is positive, negative, or equal to each other, then we have the same. We have a similar example here. So therefore, an EMF is induced by changing magnetic flux, even if the loop through which the flux is changing is not physical conductor, but an imaginary line. Imaginary line. We don't necessarily have a line to define the current loop. Okay, as much as there are some, as much as there is actually nothing, we still have induced E field. So the changing magnetic field induce an electric field at every point of such a loop. The induced EMF is related to E by this expression. So this is just the definition of the EMF, which is a closed line integral. Okay, so here let's take a look at a sample problem. It says in the figure takes R to be this length, and then dB dt is this value. So find an expression for the magnitude E of the induced E field at points within the magnetic field at radius r from the center to the magnitude of the magnetic field. Evaluate the expression for r equals 5.2 seconds. Okay, so here we would like to find the induced E field here. So of course, capital R is the radius of this area, which is 5.8. And then we would like to find the E field at R equals 5.2, which is smaller. So which means that, so this is the Ampere's loop. Okay, so here we try to use E dot ds. We try to use the Faraday's law. So, and actually E and ds should be parallel to each other, because it is a circle. So the direction of ds is the direction of the tangent line at that point. The tangent line of that point. Of course, ds can be point to left side or right side for this point, but actually you can freely choose which direction you choose. Here we just define ds is counterclockwise, So all the things should follow this direction. Yeah, because in this case we know the B field is pointing into the page and is increasing. So according to the Lorenz law, B induced is pointing out of the page. So according to right hand rule, yeah, when your thumb pointing out of the page, the E field should be counterclockwise. So we already know the direction of the E field. So it makes sense to define ds with the same direction so that you make all the things positive. Okay, so here we know E and ds are parallel to each other, which means that E dot ds is nothing but E times ds. And then E is constant over the loop because they are all symmetric. So we have nothing but E times integration of ds. So integration of ds is nothing but the circumference of a circle, which is E times 2 pi r, which is similar to what we did in chapter 29 when we play with the Mps Law. So at that time, we will usually have a B dot ds equals to B times 2 pi r, something like this. Okay, so here we also try to find phi b, which is B times A. So which is B times pi r squared. So A is the cross-section area of the circle, so pi r squared for the area. Okay, so next we would like to find d phi b dt. So d phi b dt, so this is phi b, so we have d dt and then b times pi r squared. And of course, pi r squared is not related to time, so it is actually pi r squared and then times dB dt. So it is given that dB dt is 0.13 Tesla per second. So this is nothing but 0.13 pi r squared. So this is the derivative of the magnetic flux with respect to time. So in that case, we have integration of E dot ds equals negative d phi b dt. So in that case, we have E times 2 pi r equals negative 0.13 pi r squared, which means that E equals negative 0.13 over 2. Yeah, we can actually cancel pi and pi here, this r with this r. So finally, we only get r. Okay. Or maybe we can just have E, the absolute value of E, which is the magnitude, is 0.13 over 2 r. This is a volt per meter. So this is a EMF. This is E, the E field, the induced E field. Okay, so here we try to evaluate the expression for r equals 5.2 centimeter. So here we have a E of r equals 5.2 centimeter is actually 0.13 over 2 times 0.052. So which is 3.4 millivolts per meter. So this small m is milli, this is meter. Okay, so this is part A, and for part B, here we have R is 12.5, which is larger than capital R, which means that here we have this loop outside. Okay, so in that case, we have d phi b dt, which is 0.13 pi capital R squared rather than this is small r, because for the outside part we don't have any magnetic flux, and so as no magnetic flux changing. So we only count for this yellow area. So d phi b dt is nothing but 0.13 pi r squared. Here we have 0.13 pi small r squared because this ambient loop is inside it. So we can count all the way up to small r. But here, as much as r is larger than capital R, so we cannot count through the whole circle for the magnetic flux, because for the outside ring we don't have magnetic flux there. So we have capital R here, and similarly we have an integration of E dot ds equals negative d phi b dt. So on the left side we have E times 2 pi small r, still small r, but because we need to integrate E dot ds over this path, so we have small r there. So in that case we have negative 0.13 pi capital R squared. Okay, so we can still cancel pi and pi. And finally, E should be negative 0.13 over 2, and then here times capital R squared over small r. Okay, so here we try to evaluate it with this value of R. So E of, or maybe we can just write it as an absolute value of E is 0.13 R squared over 2R. So here E of R equals 12.5 centimeter is 0.13 times capital R is 0.085 quantity squared over 2 times 0.125, like this. Okay, so this is 3.8 millivolt per meter, a slightly larger value. So far, any questions?